In the last lecture we discussed about the Dunkerley's method and comparison of the first frequency with the influence coefficient method. We derived the first expression for omega 1 from influence coefficient method. We have also explained you why this method is called influence coefficient method, because the entire system is under the influence of the inertia force caused at different modes of vibration. So, we tried to derive what we call as a delta or the alpha matrix, which is called influence coefficient matrix. So, we had used this algorithm xi double dot is minus omega square xi, which is minus k by m xi, because we know omega square is k by m, and we also know that k is 1 by, let us say, delta. So, xi double dot becomes minus xi by m delta. So, minus xi is m delta xi double dot, and we have wrote this algorithm x1, x2, x3 alpha 1 1 2 1 3 1 alpha 1 2 2 2 3 2 alpha 1 3 2 3 3 3 m1 x1 double dot m1 x1 double dot double dot m2 x2 double dot So, you will obviously see that the iteration will have to have with the alpha and m matrices. We have the m matrix for this problem separately done, alpha matrix for this problem separately calculated, then we multiplied them, we found the control matrix, which is actually this matrix. We multiplied, because essentially the alpha matrix was 1 1 1, 4 m is the m1 value, therefore, the first column has become 4 4 4 and so on. So, we got this control matrix. Now, we have the vector on both sides, which is an iteration vector. I assume the vector and keep on iterating it until the phase the one which is assumed, the one what we derive converges, we say that it has converged at this vector, and now we equated the one value as 14.32 multiplier of this one value, and we got omega 1 as this value in terms of k by m, and it compares this very well with the Dunkerley value, which is 0.4 root k by m, 39 something of 0.4, which is non-iterative, just only taking only the leading diagonal values of the alpha matrix, we got this value. Now, the question is how to take it forward to find omega 2 and phi 2. So, for this particular problem, this becomes phi 1 and this becomes omega 1. So, we got the first frequency and the corresponding mode shape, and I can say the first frequency confidently because the mode shape is all positive value. We already know for a first mode shape there is 0 crossing, therefore, this is called as the first frequency, and we now understand Dunkerley also gives me the frequency, which is a fundamental frequency, which is also tallying more or less with the value. I want to now find omega 2 phi 2, omega 3 phi 3, because this problem is a 3 degree freedom system problem. I must know the remaining omegas and remaining phis. We also said in the earlier lectures that once we have the set of phis with you, if they are orthogonal to each other, it becomes advantageous with respect to mass matrix, because the calculation becomes simple when you talk about the modular participation factors later. So, what we did is we found the vector from eigenvalue problem and then we normalized it with respect to mass matrix. We got the normalized vector, but by solving the eigensolver we do not get, or we did not get, the normalized or diagonalized vectors. We normalize them, orthogonalize them with respect to mass matrix, and we got the value. So, using that approach, now in this particular problem I want to directly derive the orthogonal vector phi 2 and the orthogonal vector phi 3, which is orthogonal going to be with phi 1 and phi 2. Now, I am going to have a matrix of phi 2, vector phi 2, that is the second eigenvector, which will remain orthogonal with phi 1, okay, and so on and so forth. So, I am going to use that principle. We already know that xi and xj will be equal to 0 if I and j are different, if xi and xa product is 1 if I and j are 1, same. Okay. So, we know that value, principle of orthogonality we apply that logic here and try to get the second vector and the corresponding frequency. Please understand in this method, in influence coefficient method, the focus or the thrust is not on omega, it is not, it is only on phi. Whereas in Dunkerley the focus was on omega and not on phi. So, you must understand the deviation in terms of the algorithm by different methods. Okay. So, here the focus is not on omega, it is on phi, that is why we are iterating phi. Similarly, since the focus for the entire set is on phi, I am trying to orthogonalize phi first and get the omega 2. Okay. Now, to get omega 2, to obtain omega 2 phi 2, we know it is a pair, okay, it is a unique combination. So, we will use principle of orthogonality using principle of orthogonality. We know, let us see what do we actually know. I have a vector which is a1 b1 c1, I have another vector which is a2 b2 c2. Let us say this vector is nothing but 1, 3.16 and 4, and the vector which I do not know, that is phi 2, is this vector which is a2 b2 c2. Now, I want to orthogonalize these two vectors either respect to mass or with respect to stiffness. The advantage of doing respect to mass matrix in this problem is mass matrix is diagonal because the degrees of freedom are marked in the location where mass is lumped. So, off diagonal multipliers will become 0 automatically. And second demerit in this problem is I do not have stiffness matrix for this problem. Okay, I already told you to verify the influence coefficient matrix and inverse of that you could have verified. So, stiffness matrix I do not have with me, therefore, I cannot diagonalize or orthogonalize these two vectors respect to k, because I do not have k, because I need k to multiply them. I do not have k here in this problem, I would have derived k, but I am not having k here, therefore, I am using m. Okay. So, let us write this condition m1 a1 a2 plus m2 b1 b2 plus m3 c1 c2 is set to 0. Why? First, why m is getting multiplied? Because I am diagonalizing this with respect to mass matrix. I do not have k, I could do with k also, but I do not have k here. Second, why this is 0? Because they are all cross products. We already know xij, ij are not equal, the product will become 0 actually, if they are orthogonal to each other. So, I am deriving a vector which is remaining orthogonal to a known vector, okay, conditionally when they are multiplied with mass matrix. That is what the condition here is. Okay. Let us do that. So, mass matrix we already have here in this problem. I will write down the mass matrix here. Okay. These are all the leading diagonal elements which are diagonally dominant and positive, remaining all are 0 in this problem. So, m1 4m, a1 1, a2 I do not know. Similarly, m2 2m, b1 is 3.16 and b2 I do not know, plus m 4 c2 set. So, let us expand this equation. 4m of a2 plus 6.32 m of b2 plus 4 m of c2 0. Therefore, I can say a2 is minus of 1.58, because m goes away in any way, b2 plus c2. Is that okay? Let us say let b2 be b2, c2 be c2, and this statement looks very funny. Okay. This is required, I will tell you why. There are 3 unknowns here. What are the unknowns? a2, b2 and c2. We also know that A2 and B2 and C2 are not independent, they are relative, because it is a mode shape. Mode shape is nothing but it is a relative displacement of Mach position for a given frequency of vibration. They are not unique. If I know one, if you know the proportion, I can remaining find remaining B2 and C2. Okay. So, I have only one equation, I have 3 unknowns, that is A2, B2 and C2. So, it is very interesting, I cannot solve this problem. Okay. Therefore, I have found out one equation. The second and third equation I am generating myself, saying that let B2 be B2 and C2 be C2. Now, you may ask me what is the advantage of writing like this. I can convert this now into a matrix form. See how I am doing it. Let us say A2, B2, C2 vector can be 0, 0, 0, minus 1.58, 1, 1, 0, 0, 1 of A2, B2, C2. Is that okay? Am I reading the same value in a matrix form? There is a minus here, because this negative is multiplied to both the values. Okay, I have got now a matrix which is new. Now, we have got to apply this matrix, multiply with the existing control matrix. The existing control matrix is this. First y we have to multiply. The answer is very simple. The vector A2, B2, C2 should remain orthogonal with that of an existing vector which is derived from this condition only. This vector is true, only for this condition. Okay. So, this is the control condition which makes this vector true. If this vector is taken as a multiplier here, then I must use this multiplier with a corresponding multiplication of this vector or this matrix. Okay. So, let us now do that. I will remove. So, I am now looking for the new vector. Instead of calling A2, B2, C2, I will call this as conventionally x1, x2, x3. Conventionally, I call this as, let us say for our understanding, phi 2. Second vector, eigenvector, which should be now equal to omega square m by 3k of 421, 484, 487, 0, minus 1.58, minus 1, 0, 1, 0, 0, 0, 1 of x1, x2, x3. For our understanding, this is phi 2. Now, I have got an iterative scheme now. I have got left hand side vector, right hand side also a vector. I do not know either of them. So, I will assume one, I will get the other one. By convergence, I will try to quantify them. Okay. First, let us multiply these two matrices and get a single matrix, which is omega square m by 3k of x1, x2, x3. Now, we know we are talking about the second vector, there is one 0 crossing. Let us assume a vector as 1 0 minus 1. It is an assumption, let. So, I am not writing this matrix back again. So, omega square m by 3k of this matrix multiplied by 1 0 minus 1. Let us see what do I get. I get some multiplier of a vector. Tell me what is the vector we are getting. What is the multiplier? Yeah. You are getting back the same vector fortunately for this vector assumed. Okay. So, it is converging because assumed one and the derived one are same. Therefore, I can equate and read 1 is equal to omega square m by 3 k, that is sorry, m by k, because this is the multiplier of 1. On the other hand, omega is root of k by m, that is the second frequency, and the corresponding mode shape is 1 0 minus 1. If you try to plot, these are 3 mass positions, let us say this is m, this is positive, this is 0, negative, you get 1 0 crossing. Okay. So, it is a first 1 0 crossing means second mode, n minus 1, so second mode. Let us try to get the third one. So, now to obtain omega 3 phi 3. Again principle of orthogonality, let A1 B1 C1, A2 B2 C2 and A3 B3 C3 be orthogonal vectors. Okay. So, this vector already we know 1 3.164, this vector also we know, this vector we do not know. So, I should say 4 m of 1 of A3, 4 m is the mass matrix M1, 1 is this value, A3 is this, plus 2 m of 3.16 of B3 plus m of 4 of C3 should be set to 0 because they are cross products. Similarly, the second equation, I am now talking about these two combinations, 4 m of 1 of A3, unfortunately these two terms will look alike. This term is from this multiplier to A3, whereas this term is m of this multiplier to A3 plus 2 m of 0 of B3 plus m of minus 1 of C3 set to 0. I have got 3 unknowns A3, B3, C3, they are relatively placed. I have got 2 equations. Let us first get these equations, 4 m A3 plus 6.32 B3 plus 4 m C3 is m here. Okay, I can take away m everywhere. I can take away m everywhere. Okay. Similarly, 4A3 is equal to C3. So, that tells me A3 is minus 1 by 4 of C3. Let C3 be C3, I can get B3, okay, which will give me so all of them are now expressed as a multiplier of C3. Okay. So, I can now generate this in a matrix form. I will retain this multiplier I will retain, I will remove this. Let us call a new vector again as x1, x2, x3, but it is phi 3, okay, which is equal to omega square m by 3 k of 0 0 0 minus 4.32 1.68 1.68 minus 303 multiplied by a new matrix which will again give me x2, x3, x3. This matrix says A3 is only a part of C3. So, 0, 0, 0, 0, 0, 0, 0.25. So, let us get a new matrix now. I will rub this. I am sorry, I am just doing some manipulation, please do it carefully. I will remove all this just to save some time, just replacing them. So, get me the new matrix. Can you get me this column? The last column. And we all know this, if any one column is 0 or only one row 0, that can be automatically put here. Okay. So, I will get only one column now. Can I say it is 0.41 positive first value? It is 0.4128, well, let us say 0.41. Next is minus 1.33. You please do not copy this, you please check. If it is wrong, then we will correct this. .67. You please check. Now I am looking for the third vector. I should have 2 zero crossings. Okay. Now I can consider this value as 1 minus 1 1. That is, from positive to negative one crossing, from negative to positive another crossing. Okay. Which is omega square m by 3k of this matrix of 1 minus 1 1, which gives me omega square m by 3k with the multiplier a new vector. Let us see whether the new vector is same as the old one. Can you give me this multiplier and the value? No, multiplier. Then you say this is 1. Okay, I will say this as 1, I will take this as 1.67. Then this is 0.25, this is minus 0.8. Okay. You can also set the other way, no problem, but why I am writing this here, because originally the last vector is a multiplier of C3. So, I am doing like this. Okay. So, now you see they are not converging, because the value is started with 1 minus 1 1, but I am getting something else. So, let us now iterate. So, 0.25 minus 0.8 and 1 of omega square m by 3k of this of 0.25 minus 0.8 of 1. So, omega square m by 3k multiplier a new vector. What is the new vector and what is the multiplier? 1.67 is the multiplier and the vector is same. Okay. So, we have converged at 0.25 minus 0.8 and 1. Okay. Now, I can expand this, say 1 is equal to, write it here. I am using the last statement, 1 of this is equal to this. So, 1 is equal to omega square m by 3k of 1.67 of 1. Okay. Can you get omega 3 as so much of k by m no, it is 1.34. Right. So, let us quickly write these values here. I think I can write down the values here. Omega 1 is this, omega 2, can you give me the simply it is k by m, I suppose, correct, and the vector is 1 0 minus 1, 1 0 minus 1, and omega 3 is 1.34 of k by m, and the vector is 0.25 minus 0.8 and 1. So, if you look at these answers of all the 3 sets, okay, there are some observations we can make with this method. Some of the observations or experience what we have in solving the problem using this method is: 1, the method is anyway iterative. The moment I say any numerical method iterative, I can always program this. Okay. 2, the method directly gives me orthogonal vectors with respect to mass matrix. Okay. 3, the values of omega and phi are given in a sequential manner. What does it mean? It always starts with a positive vector. So, omega 1, then omega 2 and omega 3. Now, you can very easily understand the whole algorithm is controlled by the assumption of a vector. Had you assumed a different vector here, you would get omega 1 as something which may not be actually the natural frequency of the system fundamental. You get some other value. Instead of say 1 1 1, you would assume 1 minus 1 0 some vector, then you will get a different omega which will not be the fundamental frequency. So, the whole algorithm is controlled with assumed vector. This is the drawback of the system actually. This will make the system or the algorithm user specific. You cannot generalize this vector. Okay. Here this is one of the, you can say, yeah, hitch in this problem. You should know how to assume the vector. So, therefore, it is very interesting. If you really wanted to find out omega 1, assume a vector with all positive. Want to get omega 2, assume the vector with 1 positive, negative and positive, etc. So, you must have an algorithm such a manner that it should lead you towards the successive frequencies which is generated. Okay. If you are able to carefully choose a vector, it will give you the values in sequential omega 1, omega 2, omega 3 nicely, no problem. Okay. This method is highly numerically stable. Can you tell me why? The main reason is this method does not invoke an inverse of a matrix or inversion, it is only multiplying a matrix. So, any method which does not ask for an inversion is always stable as far as matrix algebra is concerned. Okay. Now, this method indirectly gives me the stiffness matrix, does not give me the stiffness matrix, it gives me the indirect stiffness matrix indirectly. Maybe that is a demerit, because I want always K and M as essential characteristics of a given dynamic system. M is anyway available to me in the system, but K is indirectly available to me. Okay. This method also compares well with other numerical methods. One can say, sir, what are the other methods? For the timing we know only one method, that is Dunkerley, therefore it compares well. But I will also show you further methods also, I will discuss, it will still compare very well. Okay. The statement will be then also valid, but now we know only one method Dunkerley, therefore it is agreeing, therefore it is agreeable with other numerical methods. So, these are some of the observations and experiences what we have gained by solving a problem in this. Now, this problem essentially has, let us get back to the algorithm, turn your pages and see. This matrix not directly derived, you derived only this matrix, okay, or let us say you derived delta matrix using a linear or a series of spring system, then you multiply that with a mass matrix and you got this matrix. Now, I wanted to derive the alpha matrix directly from the given problem. See, remember the alpha matrix in this case was not derived directly, the alpha matrix is derived with delta and then multiply with m and you got this matrix. Okay. I want to derive the alpha matrix directly. Why? If you can derive the alpha matrix directly, I can always get k just by one step of inverse. Okay. So, can we derive the alpha matrix directly for this given problem? Alpha is nothing but inverse of k, we know that. For deriving Kij, we used to give unit deflection and find the forces. For deriving alpha ij, we give unit force and derive the displacements. Okay? Let us try to do that. Is there any doubt in this method? This method is well demonstrated as far as I am concerned, that for a multi-degree freedom system problem, I have taken 3, one can take 4 also, and you can try to experience. The time involved in this method is very less, though it has taken much time because we are demonstrating the method with a written example. It takes time. When you get accustomed to this method, you will be able to solve, you can easily get, and this does not require any essentially it does not require any computer program. With a calculator you can get all omegas and phis. As of now, there is no other method parallel to this which can give you all omega and phi with a simple calculator. There is no other method. Okay. So, this method is very powerful in that way. Okay. Now, let us try to derive the alpha matrix directly. First, let us get what is this alpha matrix available to me. We already have an alpha matrix of this. Can you give me this value? 1 by 3k, I think it is 111, 147, huh? 144, 147. This is what we have already with this, isn't it? So, I must get this matrix directly without the assumption of series of springs, etc. I must directly get from the first principles of alpha ij. Let us do that. Okay, individually. I am marking 1, they does not mean they are degrees of freedom, they are the first, second and third locations of respective unit forces to be applied. So, let us do that. Okay, in this method the common mistake what generally people make, when you carry over this control matrix from 1 to the next eigenvalue, you should ignore the multiplier which will give you the value. If you carry over this multiplier also into the algorithm, then you will end up in trouble. Okay, that is where the confusion will start. This multiplier is nothing but a proportional value of the vector. 1 does not mean anything. It was actually 14.32, 3.16 of 14.32, 4 times of 14.32. Since I had common multiplier, I have plugged it out. So, this is nothing but a number for me, which is an amplitude. Okay. I am not bothered about this. I am always bothered about the relative displacement of mass position when the system is vibrating at this frequency. I can either say 14.32, 14 into 3.16, 14 into 4, or I can say let us ignore 14.32, 1, 3.164. It is giving me the same physical meaning actually. So, you should never carry over this multiplier in the control algorithm, which is a common mistake what people generally do. If you do that, you will end up in a wrong omega only. Phi will be okay. Okay, you will get wrong omegas. You will not be able to know that because phi will be all right. You will get wrong omegas only. Okay, so that's it. Then you will get, you may get the value lower than this. Okay, which is not correct. So be careful about that. Okay, now let us carefully examine this. Now the second interesting problem what you get confusion is how to mark these arrow directions for the given alpha ij matrix. This is a very big confusion generally. People have this confusion, very common. This is unit force. I am writing unit force just for our understanding. Here onwards I will write only 1. I will write only 1. It means the force is unity, not the displacement. I am talking about alpha ij matrix, not Kij. Kij is force in ith degree of freedom by giving unit displacement to the jth degree of freedom, keeping all the degrees of freedom constrained, whereas alpha ij is give unit force and get the displacements. Okay. So, these are all unit forces in the respective degrees of freedom. So, let us try to mark them. Same logic as we used for k derivation. When I am trying to pull the spring down by some force, in this case the magnitude is 1, this spring will oppose the force. So, let us mark this as 3k of alpha 1 1. Now, very carefully listen this. I think possibly this way of explaining alpha derivation or the flexibility matrix derivation is not there, I think, in any of the textbooks, okay, is not there. The only textbook where you will find will be the book which I have written with Springer, which will be available by this month end on public domain. There is no other book which will explain you this. So, it does not mean that this is a unique or a very great technique to be followed in Mars and Saturn. It is very simple actually, that is the problem here, right. So, try to understand the arrow direction, how I am marking. Be exactly with me, it is easy for you. The moment I complete everything, you will not be able to reproduce this until you understand the basics. It is for guarantee, okay, you will not be able to reproduce this. You will always 100% make a mistake either in numbering them or in the arrow direction. This is for granted, you can take it granted, you will not be able to do it. You have to be exactly mesmerized on the blackboard now, then only you will know how it is done. So, I am giving a unit force here, the spring will try to pull it back because restoration. Now, I am multiplying the stiffness with displacement, this gives me the force actually, correct, because alpha 1 1 is nothing but the displacement coefficient. I am talking about flexibility matrix now. So, displacement coefficient, multiply the stiffness with displacement, because stiffness is nothing but force for displacement. When I multiply, I get the force, this is also actually a force only. So, I will write a force equation equilibrium later, right. So, I am getting an equation of that order. So, 3k alpha 1. Now, when I try to pull this mass down, this spring will push it up as usual. So, I will mark the arrow here and here parallelly. Okay. I write the value of both of them common at the center, which will be the stiffness of the spring, which is k multiplied by alpha 1 1 minus alpha 2 1, okay, alpha 1 1 minus alpha 2 1. Similarly, because this will spring pull, this mass will go down, this spring will push up, this is going to be k times of alpha 2 1 minus alpha 3 1. Okay. Let us do it here. For this unit force, start from here. So, this way and this way is always a pair. When you put here and here, because there is a common spring which connects these two, therefore, you have to mark the arrow direction of both of them. I think this we already explained in the truss problem, either it is pushing or pulling, it is not one end pushing and one end pulling, it is never, okay. So, therefore, I am marking the force in this spring actually, that is what I am trying to do. Therefore, I need not have to mark this separately, then think after a day and come to for this arrow direction. I should do it parallelly, because this is a spring force, which will be obviously the stiffness of the spring multiplied by alpha 2 2 minus alpha 1 2. Okay. Now, when this spring is pulling this mass down, this spring will pull the mass up actually. Okay. So, 3k of alpha 1 2. Similarly, when this mass is pushed down or pulled down, let us say, this spring will push it back. So, the marking is like this, which will be k times of alpha 2 2 minus 3 2. Let us apply the same logic for the third column here. So, I am trying to pull this mass down by unit force, this spring will pull it back. So, I am marking it here, pulling this back and this, simultaneously arrows are marked, which will be k times of alpha 3 3 minus 2 3. When this mass is being pulled down by the spring, so this spring will try to pull it back, which will be k times of alpha 2 3 minus 1 3. When this mass is pulled down by the spring, this will try to pull it back, 3k of alpha 1 3. So, let us write the force equations, equilibrium equations for one by one separately. Let us pick up this 3k of alpha 1 1 plus k of alpha 1 1 minus 1 2, sorry 2 1, this value, this value and this, okay, is equal to 1. Why? Because these two are upward, this one is downward. Okay. The second equation is written here, which is k times of alpha 1 1 2 1 should be equal to k times of alpha 2 1 minus alpha 3 1. Okay. The third equation is here for this mass, which is k times of alpha 2 1 minus 3 1 is 0, which implies k cannot be 0 because stiffness cannot be 0. This implies alpha 2 1 is alpha 3 1. When I substitute back here, this becomes 0, which implies alpha 1 1 is equal to alpha 2 1. When I substitute back here, it will say 3 1 plus 1 4 k. Therefore, alpha 1 1 will be 1 by 4 k, 1 by 3 k, because this goes 0. This goes 0 because alpha 1 1 is 2 1. So, this goes 0, 1 by 3 k. So, this implies that alpha 2 1 is also 1 by 3 k and alpha 3 1 is also 1 by 3 k. So, if you take 1 by 3 k common, the first column will be 1 1 1, which is as same as exactly here, it is 1 by 3 k. Okay. Let us spend a couple of more minutes to at least get this also. So, let us write this equation here. 3 k alpha 1 2 should be equal to k of alpha 2 2 minus 1 2. K of alpha 2 2 minus 1 2 plus k of alpha 2 2 minus 3 2 should be 1. K of alpha 2 2 minus 3 2 should be 0, which implies alpha 2 2 is same as 3 2. I am deriving this, I am writing this equation from the third mass, writing this equation from the second mass, writing this equation from the first mass. Okay. So, when I do this, this goes away. So, we can say alpha 2 2 minus alpha 1 2 is 1 by k from this equation. I substitute back here because this is going to be 1 by k, this becomes 1. Therefore, alpha 1 2 will be 1 by 3 k. Substitute here, alpha 2 2 is 1 by 3 k plus 1 by k. So, alpha 3 2 is also 4 by 3 k because they are same. So, the second column is going to be now 1 by 3 k common, alpha 1 2 is 1, alpha 2 2 is 4, alpha 3 2 is 4, which is as same as the second column of what you have here. Similarly, third can also be written. Now, let us quickly see where is the confusion. There are many multi-point confusions in this problem. The first confusion is, if you do not mark the arrows in combination or pair, please take it granted you will never be able to solve this problem. Okay, you will never get alpha matrix at all. If you do not mark these arrows in pair, you will never get. If what people generally do is like this, they mark the arrows with respect to mass. They pick up the mass, they mark the arrow. They say, for example, the mass is moving down, so this spring will push it up, this spring will pull it up. Okay, they have written. When they come here, they are really worried. So, you never do that. Pick up the mass, pull it down, put the pair, pull it down, put the pair, put here. Similarly, start from here, pull it down, put the pair, as it goes down, put the pair, goes down, put the value. Similarly, this mass goes down, put the pair, goes down, put the pair, go here. Then only you will be able to solve this. You have to follow this systematically, you will not make a mistake. And in all these, the second subscript will be 1, indicating the force applied to the first degree. In all these, the second subscript by mistake is also 2, indicating force applied to second degree and third degree. So, this is the second catch. So, you do not mix match the coefficients. Then of course, you can carefully write down the values and solve them. you will be able to get the alpha matrix which was otherwise obtained by assuming the springs in series etc. indirectly, but this is a direct method of finding out. So, imagine matrix methods was in position in practice in engineering only in 70s. Even 70 years before this method was in position or place, Dunkerley did this actually. Okay. So, imagine how powerful was this mathematics tool to apply for dynamics. We get back the same matrix here. So, if I invert this, which you must have already tested, it will give you the Shifless matrix. Okay, that is the problem. So, one need not have to actually go roundabout deriving this alpha matrix. Directly for the given problem, we can derive this alpha matrix. Okay. Then write down the control equation, get the iterative scheme set in, and find omega and phi successfully, depending upon how do you assume your vector. The whole algorithm is controlled by the assumption of the vector. If you are able to assume the vector correctly, you will get omega and phi correctly. So, we will solve some more problems, maybe couple of more problems by some other method, then we will compare the answers of that method with this method back again. So, this method will give you all omegas and phis in sequence. This method is controlled by the vector. This method is called influence coefficient method because it is trying to find out the influence of inertia force in every degree of freedom on the vibration system of the model. That is, it is called influence coefficient method. Okay. Alpha is the designation used in the literature for this. This method was first proposed in a research paper. Unfortunately, do not remember it now, it is available in the NPTEL reference. Please see, in early 70s people proposed this method, okay, first time in the research paper. This is not a classical method available in textbooks. This has been borrowed from the research paper. So, that is why it is very interesting and very powerful tool. Even today it is valid because it gives me, probably this is the easiest method which gives me all the omegas and phis instantaneously. Okay, this is the easiest method and it is hand computable. I mean, the calculator can do, and it is very fast. We have done 2 problems in about 40 minutes time. So, you should be able to do about 8 problems in 3 hours in a given exam, okay, like this. Okay. Any questions? So, exam is now open for dynamics. We have got about 1900 candidates who are registering for this course all over the world, about 200 candidates from abroad and remaining all are from India, about 30 to 40% are practicing professionals. So, try to register for the exam now available in Google. Therefore, your denominator will be have a competition about 2000 candidates in the country or in the world, and your percentile will indicate a true representation of your understanding of the subject in international scenario. Instead of getting a grade of S or A only with a classroom of 30, who all the 30 does not know what dynamics is, but now you compete with 3000 or 2000 people whom all know what dynamics is, then you really know where do you stand actually. Okay? That is the right way of getting a percentile for any course. So, please register for the examination and get a certificate done through NPTEL. Thank you.